circuit is a purely resistive circuit, whereas the parallel resonance circuit is also a purely resistive circuit. And we know that for the purely resistive circuit, the power loss is P equals to I square R, which we already proved in that session. The power factor for the series resonance circuit is unity, that's the one, and the parallel resonance circuit it's also unity, so it is almost 1. Impedance Z. Impedance for the series resonance circuit is minimum and given by the value Z equals to R, whereas the parallel resonance circuit impedance is very high, that is maximum. It's given by the Z equals to L by C into R. This current passing through the series resonance circuit is almost maximum, that is I equals to V by R, given by the Ohm's law. Whereas in a parallel resonance circuit, there is a very less current passing through the circuit, that is given by I equals to V into C into R by L. The frequency for the series resonance circuit given by the value F0 equals to 1 by 2 pi under root L into C, whereas in a parallel resonance circuit is given by Fr equals to 1 by 2 pi into under root of 1 by LC minus R square by L square. The magnification factor for the series resonance circuit is voltage magnification, whereas for the current magnification for the parallel resonance circuit. The nature for the series resonance circuit is Q equals to omega 0 L by R, whereas for the parallel resonance circuit it is 1 by R into under root of L by C. Where the series resonance circuit is used, it is generally used for the Q meter for the band pass filter, whereas you can find the parallel resonance circuit in the area of the tune circuit, in the filters, in the oscillators, or in the IF amplifier, intermediate frequency amplifiers. This is the comparison of series resonance and parallel resonance. Moving toward the next question, again the important examples. An impedance Z1 is 6 plus J8, which is connected with the parallel to another impedance Z2, this is 8 minus J6. The combination is connected with the 230 voltage and the 50 Hz AC supply. Just find out the admittance Y1, Y2, or your net admittance, that is Y, the current I, the power factor phi of the circuit. Very important example, many times asked in a GTU question. The data given to us, Z1 is 6 plus J8, Z2 8 minus J6. For both the impedance, the unit is ohm. V is applied voltage or external voltage, that is 230 voltage, and frequency F equals to 50 Hz. First of all, just finding the admittance Y1. We know that admittance is the reciprocal of impedance. So taking that one, Y1 equals to 1 by Z1. So Y1 equals to 1 by 6 plus J8. Now just taking the derivation and the multiplication of 6 with the opposite parameter of 6 plus J8, that is 6 minus J8. So we can write like that, Y1 equals to 1 by 6 plus J8 into 6 minus J8 upon 6 minus J8. So using the mathematical equation A plus B into A minus B equals to A square plus B square. So we can using that equation we can write like that, Y1 equals to 6 minus J8 upon 6 square plus 8 square. Now 6 square plus 8 square is nothing but this 36 plus 64, that is 100. So using that one, Y1 equals to 6 minus J8 by 100. So taking the individual, that Y1 equals to 6 by 100, that is 0.06, and J8 by 100, that is 0.08. Y1 is unit for the admittance is again inverse of the impedance, that is ohm. So instead of ohm, 1 upon ohm is nothing but the mho. Now the admittance same as the admittance Y2 due to impedance Z2, we can prove that 1 by Z2 equals to Y2 by 1 upon 8 minus J6. Again putting the putting the value of inverse parameter for 8 minus J6, we get that Y2 equals to 8 plus J6 upon 8 square plus 6 square, that is nothing but the 64 plus 36, again it is 100. So we get that Y2 equals to 8 by 100, that is 0.08, and J6 by 100, that is 0.06 mho. Now taking the Y1 plus Y2 addition, we get the net admittance, that is Y. So Y equals to Y1 plus Y2, putting the value of Y1 and Y2 here for the summation, 0.06 minus J 0.08 plus 0.08 plus J 0.06. So by taking the addition of 0.06 with the 0.08, it is nothing but the 0.14 minus 0.08 plus minus 0.08 plus J 0.06, that is minus J 0.02. So ultimately our Y total admittance or net admittance is 0.04 minus J 0.02. Now there is a solution of Y equals to under root of G square plus B square plus next bracket G square minus B square. So by taking that value, we get that Y equals to 0.1414 mho, that is the total admittance. Now into that equation, Y equals to G plus JB, where G is net conductance and B is net susceptance. So putting that value into equation of Y, we get that 0.14 is our conductance, that is indicated with the G, and minus J 0.02 is our net susceptance, that is indicated with the B. Now the total current, that is I equals to V into Y. V is the applied voltage, Y is the net admittance. So put the value of V and Y into equation of I, we get that 32.522 ampere current passing through the circuit. Now the power factor, that is cos phi, equals to G by Y. G is the net conductance, that is 0.14, and Y is the net admittance, that is 0.1414. So we are getting that cos phi equals to 0.99, which is lagging. So here we get all the parameters: net current, net conductance, net susceptance, power factor, current passing through the device, individually admittance of the circuit. The next question, the question 4b, define the following terms: form factor, peak factor, the RMS value, average value, magnetomotive force, magnetic fringing, and the impedance. One by one, starting with the magnetic fringing. Now whenever the two magnetic materials are kept with some distance and any conductor placing between these two material, now if the current carrying if the conductor is in a rotating manner, then according to the law, it cuts the magnetic lines and the current passing through that coil, and due to that the magnetic flux is generated. So that magnetic flux is generated in the air gap, and that is the amount of magnetic flux generated is known as the magnetic fringing. Now the RMS value, this is full form of the RMS value is known as the root mean square value. As we already know that the two types of current, that is DC current and the AC current. DC current has the fixed value, that is known as a constant current. AC is known as a alternating current, which has a dynamic or the random value. So to determine the effective value for the AC, there is a standard platform should be defined, because the value of AC is different instantaneous value. So you cannot predict for the value for the any time of instant. So there should be one parameter which gives you the reliable value, and that parameter, that reliable parameter for the AC supply is known as a RMS value. See, this is the common platform which gives the AC and DC is known as the RMS value, and this is the root mean square value. This is the, again, this is a common platform. So by taking any one instant, or you can just apply all the parameter for that particular instant, and you just give the result and for the whole instantaneous value for the AC circuit. The definition, it is equal to the DC value which when flowing through the given circuit for a given time produces the same heat which produced by the AC when flowing through the same circuit for the same time. So IRMS equals to Im by root 2. This is one video, very useful video, showing the different parameters for the peak factor, average value, form factor. by taking the
realized
example
that
of full wave rectifier.
is basically working during only positive half cycle. Okay, so it was providing me output during only one half of the cycle and the other half is not utilized. Okay, this is something that we do not want. Therefore its efficiency was very low. We had seen that rectification efficiency for my half wave rectifier was coming out to be around 40.6%, I guess, right? Just around 40-41% efficiency you were getting, and your ripple content in a half wave rectifier was very high. Okay, it was around 121%. Okay, so to overcome these disadvantages of a half wave rectifier, we utilize a full wave rectifier. Okay, so your full wave rectifier basically gives you an output which is something like this. Let's just say this is my full wave rectifier. We are going to look at two configurations of a full wave rectifier. We are going to look at what is a center tapped full wave rectifier and what is a bridge full wave rectifier. But before that, let's just understand what is the output that is given by a full wave rectifier. Okay, so if you have an input AC coming in, let's just suppose that AC looks like this, sinusoidal AC, then what you're going to receive as output is a wave which is going to be like this. Okay, so during positive half cycle you get the same output as input, and during negative half cycle you get your inverted input as output. Okay, so you invert this and you're going to get this. Okay, so your full wave rectifier has an output that basically looks like this. Okay, obviously what I have drawn is a very rough sketch, but you know, this is all these half sine waves are similar. Okay, it is basically your this portion of your input that you're getting as your repeated output. Okay, over here as you can see, your frequency of your output has basically doubled. Okay, this is your frequency or your wavelength over here. Okay, and at the output your wavelength is this much, which is half of this. Okay, so your wavelength is halved and your frequency of your output waveform has doubled as compared to your frequency of your input waveform. Okay, if I have to draw it nicely, then what I can do is something like this. This is my input voltage. Okay, and this is my output voltage. Okay, so obviously this is repeating and this is repeating as well. Okay, this is your V in over here and this is your V out over here. You can define your V out as same as V in between theta ranging from 0 to pi. Okay, so between theta ranging from 0 to pi, your V out and V in are same, and between theta ranging from pi to 2 pi, your V out is negative of your V in. Okay, so between theta ranging from pi to 2 pi, your V out is minus of V1. Okay, so from pi to 2 pi, your V out is minus V in. Okay, so in this way you can define your output waveform for a full wave rectifier. Okay, now if I assume my V in to be Vm sine omega t, then I have my equations for my V out. Okay, it is equal to Vm sine omega t from 0 to pi and minus Vm sine omega t from pi to 2 pi. Okay, since I have the equations, I can calculate what is RMS and average value for my full wave rectified output. Okay, either you can just solve using your regular.
Thank you.